an outline, and then underneath that is a section that says important terms. And those are going to be critical. And then there's the conclusion page, which I'll go through anyway. So I hope you've had time to look at some of those terms, because that'll save me doing a lot.
Is there a pop quiz in this?
No, but this is Mining Engineering 101. It gets pretty heavy. So this is the outline. After the introduction and so forth, first I'm going to talk about some of the history of the real prices and production volumes of minerals in general. Then there's a page of definitions, which is the one in the handout. And it's kind of turgid, so that's why I wanted you to look at that first. Then I'll talk about ore grades and resources versus reserves and life expectancies of various minerals, and then go on to this, which is the heart of the presentation, the log normal distribution of deposit sizes and grades and locations. I'll then discuss a couple of views that economists have put forward, and then the rest of the talk basically is going through some of the conditions that the economists have put on their theories. And then I will talk a little bit about some of the disruptions in the law of supply and demand that are implied by this log normal distribution and by the huge scale of mining operations today. And then I'll give a bit of a rundown on technology and some conclusions. And that's it. So the difference between us and our Paleolithic ancestors is basically that we mine. We started with stone. We started mining stone. This is a 5,000-year-old flint mine near where I grew up. It has 433 shafts with passages running off them like this, and it covers 96 acres. So it's not that small. We went on to bronze, which is copper and tin. Then we advanced to iron, and then a few hundred years ago, we started in with the Industrial Revolution and various machines, and that needs to be turned off. And this involved making alloys with some more sophisticated elements and so forth. At this point, at the beginning of the Industrial Revolution, the human race was using about 14 mineral species, mineral commodities. We're now up to, we're now here with semiconductors and very, very specific uses for very abstruse and rare elements, and very carefully devised alloys. We're up to using 85 of the elements now, almost all of them. This is another case of early mining. This is pre-European contact copper mining in Zambia. And notice that they didn't have any fossil energy, so they went in and very carefully mined only the rich copper-bearing vein in here, and they were very good at doing that. What stopped them was that they didn't have any pumps. They didn't have any energy, so they didn't have any pumps, and they were stopped by the water table. So one of the fundamental points I'm going to make is that since the Industrial Revolution began, the key enabler for everything else that's happened is fossil energy. And right now, we're at the peak plateau of petroleum production. Petroleum production has not increased since 2003, which has the interesting corollary that if the Chinese are using more and more all the time, and the Indians are using more and more all the time, somebody's using less. And that seems to be us at the moment. And petroleum, worse than that, from the point of view of most of the people of the world, petroleum usage per person peaked in 1979. So there's been, for most of the poor people in the poorer nations of the world, there's been less energy available since 1979. So I'm going to be talking about minerals availability, which is the inverse of the opportunity cost of using minerals. The opportunity cost is what other goods must be given up to obtain a given commodity. So when real prices go up, opportunity cost goes up and availability goes down. In the past, since the Industrial Revolution, the dogma is that real prices of most mineral commodities have gone down. That's not actually really true. There's been a lot of fluctuation, and it also depends on which deflator you use to get your real prices. Some deflators will show that real prices have been flat or even increased slightly. But the most common deflators used, like National Producers Index or GDP, show a slight decrease in real prices. And in my opinion, the main reason for this decrease in real prices, if it exists, has been that when the Industrial Revolution started 200 years ago, the year 1800, the European powers had just finished a huge expansion and exploration of the world. North America, South America, large chunks of Asia had not been known to them before, all of Africa. And so none of that area had been really explored for any minerals. There'd been a little gold mining in Peru, there'd been a little iron mining in Africa to make steel, and they were ahead of us in that. The Indians had even mined a little zinc. But basically, what mining there was in Germany, it was in North Wales, it was in England, it was in Poland. And so, as we came to need more and more stuff, we just went out to more and more unknown parts of the world and found some more. The second big factor is this increased use of fossil energy to replace human labor. And the third one, of course, is the continually advancing technology of mining, transportation, refining, and everything else. So in the future, we have no new frontiers left to explore. We're facing a future of continually increasing real energy prices. We have a demand for exponentially increasing production of nearly everything. Ore grades are declining, ever declining. There's the land use by mining and the extractive industries in general is going up exponentially. It's a multiple of several different exponents. And we have equally exponentially increasing external costs.
So John, I want to just challenge you a little bit.
What's that?
On your first point there, no new frontiers left to explore. You know, really is that true? Because I'm not sure that I really believe that. Because if we look at, all of the world's oceans, right, and minerals available underwater. Now, granted, it's more complex, but that's really not been touched on. Secondarily, let me just point out, space exploration and the availability of minerals on other planets.
Well, there's basically a two-part answer to that. One is as far as the ocean goes, and I talk about the ocean in my ocean mining in my last slide.
But I don't want to wait till there.
No, okay. But basically, are the external costs of mining toxic substances from very wide areas on the ocean floor, because this is a very thin layer, are they acceptable?
Yeah. No,
That's number one. And number two is, can we afford the energy cost? Because that's going to be the other big issue. And as far as outer space goes, I mean, we were just talking about mining asteroids, and that maybe is a remote possibility. But again, the energy cost and the resource cost to get to anywhere significant in outer space is just, I think, going to be beyond the human race shortly.
Well, but with continually advancing technologies, which is one of your other bullet points there, I think that it's a perspective, right?
But I think energy is going to defeat us. I mean, we use these continually advancing technologies are using more and more energy, and that's going to be a real issue that we have to deal with. So anyway, we can. That's a hugely valid point, a very good question, and people can really have very honest differences on that one. It really depends. I think it depends on whether you're a pessimist or an optimist. So this is a couple of things on external costs. In a real sense, any non-renewable resource extraction is harmful to the planet at some level. Those little flint mines 5,000 years ago destroyed 96 acres and probably quite a bit around that. And nowadays, it's huge. This is the Athabasca tar sands at Fort McMurray, which is hydrocarbons rather than minerals, but there's the Athabasca River, which is a huge river. There's a tailings pond, and that's a huge area of disturbance, and everything on that slide is being deforested. And this is the typical kind of truck that is used in operations like that. That truck holds 350 tons of rock. So
There are people there by the tires, aren't there?
there are. That's a person's head right
Those
there.
are-
How tall is the tire?
Not even half of the
40
tires.
foot tall?
The tires are about 14 feet in diameter. Yeah. So, with this exponentially increasing damage to the earth, the trouble is that we don't know where are the thresholds for permanent, irreversible, and runaway damage to the earth. I mean, you know, we have some ideas, but nobody really knows where the tipping points are. But we know there are tipping points. We know that there are many forward feedbacks built into the Earth atmosphere and Earth-ocean systems, and if we pass them, we're going to be in trouble. And that's the point I just made. 3 or 4 exponential functions multiplied together give you the environmental consequences. So what I believe is that sometime within the next 100 years, starting from now, within the next 100 years, we need to make do with an order or orders of magnitude lower resource consumption per person. World population is still going up and still will go up probably for another 30 or 40 years. We have to learn to live better with less material things. I don't know how you do that. I mean, I have no idea how to do that, to make that transition, but I think we
We're
have
not
to
very
do
good
it.
at that.
Are you talking about all mineral resources or even some of the oil and natural gas? Are you lumping those into?
Well, we're going to be forced to do with less oil and natural gas. But I think it applies to everything extracted from the earth is the real cost is going to force us to use less, but we need to foresee that and be proactive about it.
Well, but I think it actually goes beyond that, because we need to reduce our consumption at all levels for everything.
Yeah.
Because where does that stuff come from? The base materials, the raw materials are
Right.
extracted from some natural deposit or resource
That's
in
right.
large part.
Yep.
Yeah, actually, many years ago, when we talked to this group, I discussed this in terms of closed cycle systems.
So, and the other thing I want to say while we're looking at this slide showing this huge equipment and this real damage is we shouldn't blame only the extraction companies for the damage we see. The real driver is the demand that we make for these materials. The only real thing we can blame the extraction companies for is if they don't follow best practices. If they do things that
Well, but how do you overcome the rare minerals that are needed for,
I don't know.
so many computers and
I don't know.
cell phones?
We'll get to that. We'll get to that.
John,
Oh, so skip the slide.
shall we take just a moment's break for?
Yeah, this is actually a good place because that's on the end of the prologue, so it's a good place to stop. Thanks. But this top slide shows the current price of oil decreasing, then really going up during the OPEC crisis, coming back down and going up again after 2003. It shows the production too, where we were rising on an exponential curve. We economized during the OPEC crisis. The exponential rise started again. This is grossly oversimplified. And now we've reached this plateau at about 30 billion barrels of oil per year. The real price is, you almost can't see it for oil, is way down here. Comes sharply up, back down, and now is reaching levels that it's never even attempted to reach before. But it was dirt cheap in real terms up until 1977. The copper price is much different though. I mean, people talk about an overall decreasing trend, but what's really happening here is there's some sort of cyclicity with about an 80-year period. And I'm going to talk about the reasons for some of that. You can also see price spikes in wars here, the end of the World War II period. And I'll especially talk about this long decline from the early 70s onward. These yellow bars are periods when there was some sort of control of the market through regulation or through monopoly pressure.
You mean worldwide market?
Yep, these are all worldwide. Everything's worldwide on this. Now, these are different. Now, this one here is iron ore, and there's a faint blue graph. I'll trace it out here. It goes like this. It's exponentially increasing, and you can see how in the last, both for copper and iron ore, we have this really steep rise when we get into the 21st century. It's really taken off, but it's exponential all the way. And then there's almost constant real price with some sort of bumps on it, but not really decreasing. Again, the other one here is bauxite. Now, bauxite is different because aluminum was not used by the human race until about 1900. My mother got a set of aluminum pots and pans for her wedding present in 1939, and she got them because aluminum was sort of the latest thing. It was like giving somebody pure copper cooking vessels in those days. So here's aluminum, not even visible down here in terms of production, and then this very, very, very sharp rise. And again, in this case, it's a more obviously discernible decreasing price, because when something is rare and very expensive to produce, of course, the price is high, and as we've gone through the 20th century, we got more and more efficient at mining and processing aluminum. This is another thing. We think of cement, you know, as the thing that's around us all the time. Nothing glamorous about cement, but in fact, cement's like aluminum. The Romans knew about cement and they used it, but we didn't really use much cement until 1900. And then we started surfacing roads with cement, building houses and skyscrapers with cement, using cement for slabs. Before that, cement was building before that was timber, stone, brick, not cement. So cement has had a rise very similar to that of bauxite production. And the price, if not showing a slight decrease, is really constant in real terms with cycles, which are related, very much in this case, related to these economic events.
So you talk about limestone. Limestone.
Yes, limestone mining and burning to make cement. So I'm going to leave those. I'm not going to talk about the last one. The last one is platinum, and I put it up for contrast, but I know I'll be short of time. So here are the terms you've got, and the only thing I want to say about this is resource base is the total quantity of an element present in the whole entire Earth's crust, 40 miles deep on average, and everything above 0 ppm, or ppt in some cases. So when we talk about how long the resource base will last, which we're going to, it's meaningless, because we're never going to recover the last 1 ppm, 2 ppm, those are parts per million, by the way, ppm, from the rocks. It's an idea, a concept, but it's meaningless in real terms. But you see it thrown around all the time. Inferred resources are resources above some grade, some content of the element that we think on geological grounds exist, but we've never gone out and measured them. So this is the kind of number that the US Geological Survey puts out for, say, oil in the Bakken or copper in the Andes or something like that, the ultimate recoverable resource. Indicated resources are, on the other hand, are something usually with a higher grade that somebody's gone out and drilled and measured and sampled. And these resources are probably orders of magnitude, always orders of magnitude less than the resource base. These are probably an order of magnitude or 2 orders of magnitude less than inferred resources. From indicated resources, by thorough drilling based on a very scientific sampling plan, you can get to reserves. Reserves are defined as rock that is valuable enough to be mined at a profit now. And it's very expensive to turn resources into reserves because you have to drill many, many thousands of feet of core, and you have to analyze it and log it. And drilling core costs around $100 a foot these days. So mining companies don't usually drill the reserves out for more than 15 years ahead of their production. Then these other things are not so important except this concept that going from a lead to a prospect, if you have 10 leads, 10 indications of mineralization, going to a prospect, it'll give you 1 prospect that is worth drilling or sampling in detail. And if you drill or sample 10 prospects, you might get 1 deposit, the definable accumulation of minerals. 10 deposits might give you 1 mine, or something that's now mineable and economic. So you need 1,000 leads to end up with 1 mine. So you need a lot of land, you need a lot of resources. Grade is the percent of the rock composed of the mineral you're interested in. And ore grade is the percent of the rock that is the percentage which, when it's in a rock, makes that rock economic to mine. So ore is rock that can be mined at a profit right now. And those are critical concepts to bear in mind because you'll see people throwing reserves, resources around, and they're not careful about what they mean, and they come up with very funny conclusions. So here's ore grade for selected elements. The Clark is the average abundance of an element in the Earth's crust, the average. Remember that the resource base, though, is not what's above the Clark, it's above what is 0. So, and the Clark of concentration is the ratio between ore grade, something that's profitable to mine, and the average. And so ore grade varies. If there's a depression, ore grade goes down. If there's an increase in wages, real wages, ore grade will go down. If the economy is booming and mineral prices go up, ore grade goes down. So it changes all the time. So we look at these things. Aluminum is one of the most common elements in the Earth's crust. To get ore grade, it's only 4 times the average. Actually, it looks more like 6. The guy that made this table must have miscalculated. But the trouble with aluminum is it's highly energy intensive to get from the ore. Iron is much less energy intensive, but ore grade is 12 times the average abundance. Titanium, which we'll be talking about, is 23 times. Titanium, again, is relatively abundant, but very expensive to get out of its minerals. And then we get down, we can run through all these. These are the traditional elements that we've used since the beginning of the Industrial Revolution. Then we get down to lead, chromium, tin, and silver. Thousands of times they need to be enriched before they can be mined. And a sort of rule of thumb would be that the larger this number here, the larger the Clark of concentration, the smaller the typical ore body that you can mine would be. If you don't have to have, because basically to make an ore body, the Earth has to put in energy. Ore bodies come from circulation of hot water driven by volcanic eruptions and all sorts of other things. But basically, to concentrate something in the Earth, it's going against the law of entropy. So it requires a big energy input. And the more that Clark of concentration is, the bigger the energy input, and therefore the smaller the likely deposit. Now this is life expectancies of world reserves, and you can see that for most of the, except for the very common ones like coal, is very easy to map out where it is. Aluminum is very easy also to map out where it is. It basically forms in soil in the tropics. But these ones that have to be explored for, and copper, see, there's at 0% growth, there's somewhere from 17 to 40 years of reserves in the ground, and at 2% it's 32, 15, and at 5%, 22 to 13. So, as I said, mining companies don't bother to go to the expense of drilling out the ore unless they're about to use it. Notice here I've highlighted aluminum because of the growth rate, 2.9%. That's pretty, that's in between these two, but it's getting up there. And I've highlighted lead, and I would have highlighted tin too, because they have negative growth rates. Lead, because it's poisonous, and we have replaced lead in lead paint with titanium, a case of substitution, and economists love that. And tin, we have replaced tin cans with aluminum cans. But in both cases, the energy input to get those two substituted minerals is much larger than the original. So this is life expectancies of the resource base. This is everything above zero in the Earth's crust for these same minerals. And what you can see is, there's, for aluminum, the resource base, 10 to the 18 times as much aluminum in the Earth's crust as we're producing every year, so it would theoretically last forever. Same with iron. Some of these are lower, and this is how long they would actually, this is the actual production, and this is how long they would last at that production. So we've got 1 million years, 100 million years there. All of them are in the millions of years, except for aluminum, which is in the billions. But when you start putting a growth rate on that of 2%, all of a sudden, you've gone from 89 billion years to 1,065. With copper, you've gone down to 736. With nickel, this one, you put 5% growth rate, and nickel has come down to 229 years. That's the length of the American Republic, right? Copper is the longest one of them now, aluminum 444. That's less than the time since Columbus discovered the Americas. That's about the time since the King James Bible was first printed. But what are the actual growth rates? Well, they're not 5%, thank goodness, but a few of them are above 2. So they're above this number: aluminum, copper, natural gas. I don't want to talk too much about that. Silver. Notice the ones that are above 2% are the ones that conduct electricity real well. Silver is the best conductor of all. So we're using things in the electronics industry here. That's what's driving that. Now I want to come to a really critical point, and that is ore deposit. Almost everything in geology is distributed log normally. So this is a log normal distribution here. And what you can see is this is the 2 standard deviation point. And that 2.3% of all occurrences on that high tail is, the threshold there is 4 times the mean of the deposit, of the distribution. So if you had a normal distribution that had the upper tail starting at 4 times the mean, an awful lot of the values in that normal distribution would be negative, right? And so this, to convert a log normal distribution into a normal looking distribution, you use a log scale on the bottom here, and then everything comes, looks the way it usually does. But it doesn't alter the fact that this is a logarithm of 2.5 here, and this is a logarithm of 2. So, sorry, this is the logarithm, yes, the logarithm is 2. The implication of this is that most of the world's mineral supply, for whichever mineral you want to talk about, except for maybe iron and aluminum, is the major part of the mineable, the economic part, is in a very few, very large deposits. And what makes it even worse, and I've only found this in one place, a series of papers by Brian Skinner, who was a very intelligent man he used to edit Sigma Xi, if anybody knows what that is, at Yale. And he talked about bimodal distributions of minerals. There's the distribution of the ore bodies, and then there's the distribution of the rest of the rocks. So I've extended that here, and I'm talking about a trimodal distribution. You have the distribution of the rest of the rocks with the Clark coming in here. Then you have some very large low-grade ore bodies with a distribution like this, but still log normal. And then you have the ones that we used to mine 100 years ago, the rich high-grade veins, still with a log normal distribution, but a much smaller amount of metal. And so it's critical, and what we've been doing through the Industrial Revolution is progressing this way with our minerals extraction, progressing from right to left. And this is just further details on that. And here is, for copper, here are some of these big mines. The one single mine of Escondida, La Escondida in Chile, produces 8% of the world's production of copper. The Chuquicamata, which is another huge mine in Chile, 6%. The Grasberg mine in Indonesia, owned by our favorite person we love to hate, Freeport-McMoRan, is 4% of world production. So the top 3 mines are nearly a fifth of the total world's production. And in countries, Chile alone is a third of the world's production, and the top 5 countries are nearly 2/3 of the world's production. So it's a highly concentrated market, and that follows from the nature of the distribution of ore, and it applies to all minerals. And then here is an example. This is a cumulative probability curve log with a log scale for copper, and the 90th, now this is the 90th percentile and the 10th percentile. Look at all these deposits down here below the 10th percentile, very low grade, but these are the ones, the high grade ones, because this is not high grade, sorry, high tonnage. This is tonnage here. So these are very small deposits. The large ones, the top 10%, are way out here, and this threshold is 6.3 times the median size. So they're a lot bigger, and the really big ones are much bigger. So this is a hard graph to understand, but it's very instructive. 45% of the deposits of this type, these are gold deposits, I do believe. Yep, gold deposits. So in the Comstock epithermal vein, that's the stuff at Virginia City, Nevada, very similar to the stuff in the Mother Lode in California. Those things, 45% of them fall between this grade and this grade, which is like 30 ounces a ton down to 3.2 ounces a ton. And the metric tons of ore are between those limits, between 0.1 million and 10 million. But the elephants, the Comstock itself, is way outside that. Way outside. The grade is kind of average, but the actual tonnage is up at nearly 10 million tons. So we mined those all out in the 19th century, the gold rushes. 1850 to around 1920, gold was held, price of gold was $24 an ounce. And then we kind of ran out of those. But fortunately in 1897, the Witwatersrand in South Africa had been discovered. And these are truly huge deposits. Every one of these lines represents an order of magnitude increase in the amount of gold in the deposit. So this is 1 ton of gold. If a deposit's along that line is 1 ton of gold, 10,000 tons of gold. The Witwatersrand deposits are right up there, 3 orders of magnitude larger than the Comstock ones. Huge, wonderful, excellent for mechanized underground mining. The elephants, the distribution is much tighter. The elephant is just on the edge of the ring of the 45% there. So what happens what happened then was we mined these things down until we were underground, 12,000 feet underground, 2.5 miles deep. We're getting rock bursts. It's getting very dangerous. It's getting too hot for humans to work. The costs are going up. The human costs are going up. So the price of gold, eventually the United States government had to stop holding the price of gold at $35 an ounce and let it rise because there was no gold at $35 an ounce. So the price rose up almost immediately to around $300 an ounce. And that caused a gold rush in Nevada. And people, these two types of deposits, which are very similar, scores of them were found in Nevada and opened up. But notice, it takes, if you take that elephant and those elephants, it takes nearly 100 of these to make one of those. If you take the normal sized ones, not the elephants, it takes nearly 1,000 of them to make an average Witwatersrand deposit. So we got gold mines all over Nevada. Nevada is now the biggest gold producing area on the planet, but it's not increasing the supply of gold tremendously significant. And where do we go from here? There are no more, oh, and the other thing I wanted to say is the grade here is about 1/8 of the grade of these two types. So to mine these, you have to shift 8 times as much dirt for every ton of gold. So where do we go from there? Well, we don't have any more gold deposits. We're now going to have to move to the gold we get as a byproduct from mining copper. And the grade is again about 1/8 or 1/10 of what it is in a gold deposit. There are some huge porphyry coppers. This is Escondida and Chuquicamata out here. But the supply of gold then becomes dependent on the supply of copper, unless the price of gold gets so high that the price of copper, that copper becomes the byproduct. So, uh-oh, I touched something I shouldn't have touched. Maybe it'll go away.
No, luckily, John.
Escape.
Just hit enter.
Hit enter.
There we go.
Okay. So there are two classical economics views of these sort of things. There are people like me who this particular economist Beaujolais calls the physicist, the physics view, where mining engineers and geologists, and we keep worrying about whether we're going to run out of stuff, right? And we calculate reserves and we calculate resources and we say how long it's going to last. And these two guys, Gray and Hotelling, were economists, and they said, forget about all that, let's just assume deposits are a fixed size, we're not going to find any, we're not going to do any exploration. What's the metal worth? And they calculated a very neat theory, which is irrelevant, so I won't talk about it anymore. But then the majority of economists take this viewpoint. Minerals have not limited society's welfare in the past, nor do they have the potential for limiting the welfare of mankind in the future, so long as certain conditions are maintained. So they ignore everything that I've said so far, and will say, and the conditions are the internalization of external environmental damages.
What does that really mean?
What that means is pricing into the product all the damage to third parties and the earth that will be caused by getting it out.
We're not doing that.
We're not doing that. No, right. Access to the Earth's crust for exploration. Free, unfettered access to the Earth's crust for exploration. Well,
We don't
with
have that either.
a lot of limitations on that. Worldwide trade access to raw materials. Prevention of market control by either sellers or buyers. And I just,
Oh, right, yeah.
Right.
Like that's possible.
okay. If these rules are followed, markets will provide supplies and ration use so that minerals and materials will be available to meet society's needs without significantly increasing costs for a
That's
long
an academic right there.
forever, right? And that's the accepted dogma. That's what you hear from economists. That's what you read in economic journals and in some politicians' statements. It's all there. All we have to do is go drill it, go dig it, whatever. So these are the limitations. You've already come to the conclusion. We're not doing any internalization of external costs. How can we do it? We can tax, we can regulate, and we can have cap and trade systems. And not only do the companies complain like heck about taxation and whatnot, the public complains. We don't want to pay more for our whatever. Regulation, oh, big government. Cap and trade, heresy. You know, so we're not going to, in this country at least, we're not going to go anywhere with any of those things for a long time. Access to the Earth's crust for exploration, the next slide goes into this a bit, but cities are expanding, farms are maximizing the amount of land they use, wilderness areas and parks are being created all over the place, and up in the northern areas, the permafrost and ice prevent us from accessing stuff. So we don't have access to the Earth's crust. worldwide trade access to raw materials, well, there are haves and have-nots because the distribution in space of deposits is what I call lumpy, uneven, none here, lots there. And some people don't play by our rules, particularly China, so we don't have access to big chunks of the earth where people don't want us to go and either explore or own mines or whatever. I mean, we've had expropriation of mines in Chile 30 or 40 years ago. We've had expropriations in Brazil and so forth and so on. And then prevention of market control. Well, we got this log normal distribution with very few, very high grade, very large deposits. It's very capital intensive, which makes it even worse with $25 billion needed to open some new mines, new porphyry coppers and things. So this is wonderful opportunities for market controls by companies, De Beers, Rio Tinto, Rio de Valle Doce, and by countries. So the conditions aren't met. And I had another slide with other things that weren't met, but I decided to leave that out. So here's the one fundamental rule, which we've already sort of beaten the bush around here, is if you halve the grade of ore, you have to double the amount of rock you dig out to get the same amount of stuff. You also, for almost all commodities, if not all, you grind it up into 300 mesh slurry that you can then run through a flotation plant, and you have to get rid of that stuff. And generally speaking, you can't put it back in the ground, and you can't put it anywhere. You have disasters like Aberfan in Wales, which was coal slurry. You have disasters like the Hungarian bauxite thing in 2011. The stuff is unstable, nasty. You don't want it around. When you get a sedimentary ore body or a tabular ore body of any kind, the deeper you go, the more overburden you have to take out in relation to the size of the ore. So you get this one I've shown, we're taking out 12 times as much white stuff there as you're taking out ore. So that's another multiple. That's on top of the diminishing ore grade. You've got an generally increasing stripping ratio everywhere. This is called stripping ratio. Furthermore, with an open pit mine or an underground mine, you generally have to dewater the whole area, otherwise you run the risk of being flooded out all of a sudden, which can cost a lot of life. So you make a big dewatering cone and you end up with all kinds of problems for the surface owners, like the people around Bastrop, because of the lignite mines. And then finally, the mining itself, the trucks, the grinding of the rock, and the tailings particularly, is a lot of toxic dust blowing around, causing, lung cancer and other health issues. And not finally, there's also acid mine drainage, which you can't avoid if you're mining a sulfide ore.
So how do you do the water? How do you do that? So how do you pump it out?
Yes, yep.
Water table?
Yep, you pump it out until the water table's below the mine. One mine I worked at in Zambia back in the 1960s was pumping 90 million gallons a day.
Where were they putting it? Where were they putting the water?
In the nearest big river,
Oh,
in the Kafue River. Yeah.
they're pumping fresh water and just sending it out to sea.
Mm-hmm. Mm-hmm. Well, there's no way of using it, so. And that's probably not the maximum being pumped out. This, in Western Australia, some guy has tabulated all of these environmental costs for their mines. It's about the only place that I can find that they've done it. And this is kind of a compound graph, but this is the amount of ore milled, mined, taken to the mill, and ground up. And while they were mining these high-grade things, this is the grade, while they were mining these high-grade things, it was a very small number. And then all of a sudden, in the 1980s, it went up. Technology, increased demand for gold. Remember, gold went from $35 an ounce to 300, 800 eventually. And the amount of waste rock they mined, this is the waste rock that he could crank. This is the percent, this yellow thing you can hardly see was the percentage of mines reporting. So to get the total amount of waste rock, you have to multiply that by the inverse of this, which is 30%. So this is 3 times as stripping, 3 times as high as up on the ceiling. The waste rock went astronomically high.
Where is it now? Where is it?
Piled around the mines.
Inside the mine?
No, all around them.
Stripped out.
Sometimes, some kinds of mines, some kinds of environments, you can push it back into the hole for open pit mining. Sometimes 100 years later, because you're mining that mine maybe for 100 years, and eventually you push it back in. For underground mines, you can never get it back in because after you've ground it up, it's bigger than it was when you took it out. So it won't go back in. Smelting and refining, I don't have as much experience with this as I do with the actual mining, but some famous cases of water pollution, this is seawater pollution, cadmium from the Imperial smelter in Bristol, that nobody could eat the shellfish for a few decades. Mercury poisoning at Minami Bay in Japan killed a lot of people, same reason that was. Soil pollution, I've actually worked in some cases like this. Ducktown, Tennessee was a copper smelter. The area around it was completely deforested. No tree would grow for 100 years in a radius of about 10 miles around the whole thing. And they put in an enormous amount of money and they've succeeded in reforesting it now. The Coweta Forest Research Station is 80 miles downwind of Ducktown, and I did a soil study there and I found 1% sulfate ion in a narrow layer of the soil, which corresponded with the distance that that iron would travel in the time that smelter had been operating. When I worked at Nkana in Zambia, we had one of the biggest and one of the most efficient copper smelters in the world. But that smelter was putting out 550 tons of copper sulfate a month. It was producing 300,000 tons of copper a year. And the losses were 2%. And if you work that out, it comes to about 550 tons a month. The result was that downwind where I was working, we had 0.5% Cu everywhere in the soil, and the trees were beginning to die off because no tree will survive that. Rockdale, Texas, we have the same sort of thing. I think it's Rockdale that I've actually read about cases of fluorosis from the aluminum smelter. So, and solutions. Well, we already went through the solutions: taxation, regulation, cap and trade. Apart from the philosophical difficulties, we don't know the total environmental costs. We have not come up with accurate ways of calculating any of that stuff. It depends on value judgments, which are different for everybody. Any kind of scheme that involves taxation or regulation it's subject to political influences and corruption, especially if it's taxation. So we're not getting anywhere. This is the molten slag coming out of that huge smelter at night. Gorgeous scene at night. But, so here's a model that I made up. I don't know, other people may have made it up, but I worked this out for the growth of total external costs. And what the first line here, I've kind of broken it up into the fundamental units. The rate of increase of external damage or environmental damage per year is equal to the rate of increase in the population, the rate of increase of GDP integrated across everybody in the world, times the rate of increase in the intensity of use. So that would be a negative number for tin and what was it? Anyway, and then
Tin and copper were
no, it wasn't copper. Tin, lead, of course, lead. And then that's multiplied by the increase in the average stripping ratio per year, and divided by the decrease in the grade, because that's going to be a number less than the 1. Now, I mean, I wanted to do it this way because I wanted to point out the things that influence it. Population growth, right? That's as long as that's growing, we have difficulty cutting back. As long as GDP is growing, even if it's negative in large chunks of the world, we have trouble cutting back. The intensity of use means that these rare metals that we're relying on more and more for electronics are going to be more and more important in this equation. And of course that just goes up. So, but in fact you can lump these first 3 terms together and call it just increase in production, because that's tabulated, that's easy to get hold of, going up somewhere 3 to 10% a year depending on the element. but it hides these things, times the increase in the stripping ratio over the decrease in grade. So then I went and I looked where P, that P that's we're looking at the rate of increase of is total world production of a given commodity. So then I went and looked at various commodities to see what some of these things were. And for some of the big ones like bauxite for aluminum and copper and iron over the last few years before the recession started were 10% a year. And I'm guessing that the increase in stripping ratio is about 5% a year overall, because it's going to be much bigger for individual mines, but some of those will be being phased out in new mines starting with lower stripping ratios. And then the grade decrease, I actually looked at numbers which are available for that, and it's about 1.5% per year for many commodities. So if you work that out, you're getting a rate of increase of environmental damage. It's really a rate of increase of the amount of rock moved, but I'm treating that as the determinant of all the other damage, right? The more rock you move, the worse everything is. 17% a year, doubling time of 3.3 years. Last year in the world, we completely destroyed by mining an area the size of West Virginia. If we go 33 years into the future, no, 35 years into the future, we'll multiply that by 2 to the power 11 or so. 2 to the power 11 is 2,000. If you multiply it by that, it's more than half the land area of the world being mined out every year at that point. So that's the size of the problem we're facing. And you know, it's like the old environmental textbook thing of the duckweed on the pond, and the duckweed is doubling the area of the pond it covers every year. And if you go for 100 years and there's really no visible difference, and then the next year it looks a bit bigger, and the next year it's definitely bigger, and the next year after that is half the pond, and the next year after that the pond's gone. And that's what we're facing because of multiplying these exponential trends together. And of course, I left out the recession, so that maybe exaggerates it a bit, because there wasn't a long enough time scale to use to include the depression, and that would have given a really serious negative. So this is worst case, is what I'm saying. This is worst case, and this just summarizes that. Only 15% historical land disturbance has been restored in Western Australia, which has fairly strict laws. Only 1/3 of the disturbed land we'll be talking about is the mine itself, and another third is tailings dams, and another third is these dumps we've been talking about. And currently in Western Australia, they are rehabilitating about 70% of the land that is mined every year, or the equivalent of 70%. And this is the ranking of commodities by the amount of land they disturb every year. And look at number 1, sand and gravel. So I know that's probably hard to read from the back, but sand and gravel is by far the biggest culprit. And you see that. You drive to Houston, everywhere you get anywhere near the Colorado River, it's being dug up and the gravel taken out. Anywhere there's, and then you get down to the Brazos River and it's the same thing. Every available source of sand and gravel in Central Texas is being used, and that's worldwide, and it's increasing. And it's getting to be a significant factor in building costs, because as cities grow and as nearby sources of sand and gravel are used up, we have to go further and further away, and sometimes we're going 100, 150 miles away to get sand and gravel.
Is that the same sand that is used for oil extraction?
No, this is regular sand that goes into cement, goes into driveways, concrete. This is all these uses. They're really cheap stuff, but if you if you read around a bit, you'll find that it's a very serious concern for cities, is where they're going to be able to find enough sand and gravel to keep building a city. Coal is the next one. Stripping down West Virginia and East Kentucky. Funnily enough, diamonds is one of the worst. I don't know how it got in there, and I have to check my numbers there. But that next one, again, is a cheap mineral. Phosphates, very cheap, used for fertilizer. but used these days, get this, the Green Revolution. We put off Malthus's predictions by having the Green Revolution. But what the Green Revolution depends on is phosphate. And that is one of the major culprits now in destroying the Earth's surface.
Why?
Because it's so huge, it's so vast.
No, why is it the ingredient in the green?
It's fertilizer, superphosphate
You gotta
fertilizer.
wear the land out in one season.
Yeah,
So you have to keep pouring fertilizer, and every time you extract
yep,
all of that mineral through
Yep.
planting it, over planting it, then you have to
Yep.
put it back in chemically.
and then there's the limestone for cement, which is so visible to us whenever we go to San Antonio or up to Round Rock. And then we get into the traditional, there's crushed rock too, but we get into the traditional minerals then. Copper, chromites, iron ore, lignite, boron, bauxite, petroleum, clays. These are the traditional things. But, you know, everything I've said has been focused on metals, but the real culprits are not so much the metals. It's the non-metallic minerals and the fuels, coal and sand, gravel, cement, and all that stuff. And we have much more influence over those things than we do about coal and diamonds and gold and so forth, because that's all around us everywhere. We can pressure our local governments to do something about that if we so feel inclined. I want to try and rush through this, but this part of the talk is about the lumpy supply curve, or stepped supply curve. Ore deposits are, and also about the restriction on land. If you make a mineral deposit inaccessible, such as the Arctic National Wildlife Reserve, you can't replace it. You can find another one somewhere else if you're lucky, but if you run through that and you need something game, you have no choice. You know, there also has to be favorable geology to have any kind of deposit. You can't move a deposit from somewhere like you know, New Jersey, where nobody wants it, to North Dakota. You lose it if you don't use it in New Jersey. You lose it, and that's one of the reasons why some countries have lots of mineral deposits and some have very few, which leads to the strategic minerals problem. And then there's this whole business I went through of access to land, the 100 leads and prospects and so on. And this is a diamond mine in North. This mine is 2 or 3 years old. Look at the scale of that operation. 2 or 3 years. Diamond
What is it on?
diamond mine in northern Canada.
How deep is it?
It looks to me to be about 400 feet deep. I could count those benches, 40, 80, 100, no, it's about 350. And here's the land, here's some of the restrictions on land. This red land here is land that's already intensively used by humans and can't really be used for any kind of extractive industry. The dark blue is forest land. So, and you know what a howl there is anytime you put any kind of extractive thing into tropical forests or even temperate
Well,
forests.
I'm surprised that on the east coast of the US, it looks like that's mostly blue instead of red.
Yeah, I'm sure this was generated by doing a classification on satellite imagery. And the East Coast is all, forests are all regrown in the East Coast in the last 50 years since
Well,
1900.
blue and-
Yeah, but it's heavily populated.
Yeah, it's got
So
lots
you
of
wouldn't
red.
be able to do
You've got
that.
lots of red there, but what's showing up is,
Excuse me, as a New Englander, Maine is the most heavily forested state in the
I
country.
recognize
And
that.
Massachusetts is the third most heavily forested state.
yeah.
I recognize that, but
Okay.
there's still heavy populations along
Yeah,
that
right.
east coast, and I'm asking why that's not showing up.
It's not showing up because I'm sure the way the data was derived. So the data is actually underestimating the scale of the problem.
Right.
So, and then this light blue is the frozen lands that you can't use. So what's available for exploitation is green,
But
basically.
that's gonna be fixed though, with global warming. We'll be able to use all that, no problem.
Okay. And then this is Idaho, which is one of the major was one of the major mining states in the United States 100 years ago. And the green is available for use. That's about 20% of the state. The white is useless land, mineralogically useless land. It's recent lava flows, essentially. And the yellow is restricted areas, and the red is not available at all for mining. So only about 20% of the land is open to mining, and many, about half of the old mining districts, which are these darker red areas, are about half of them are in the restricted area. So it means that land that we know, half the land in Idaho that we know is mineralized, we can't look at because it's either a national forest, wilderness area, park, or something. So I'm not really complaining about that, but what I mean, you know, it can sound vehement, but what is important is that we've made a value decision. We've cut off some of our access to future minerals in favor of preserving the environment. And personally, I support that. We have to realize there are consequences. So on strategic minerals, that's how much, these are percentages in this column, from 0 to 100. We import about 60% of our petroleum. So that's a benchmark. We know how much grief that causes us. We import 100% of all those minerals. Asbestos, cesium, fluorspar, graphite, manganese, rare earths, quartz, niobium, tantalum, you know, all those things, 100%. These we import more than we do, a higher percentage than we do petroleum. So titanium and cobalt and potash, which is another fertilizer mineral.
Where's uranium on the list?
Uranium is, no, good point. Uranium, I think,
I would have thought it would have been higher than petroleum.
On the left side.
does anybody see it? It's for sure on here, I just don't see it.
On the left lower table.
Yeah, it's the most critical.
Yes. Yes, it's a critical. These are the ones that the U.S. government regarded in 2007. Actually, the National Academy of Science regarded as most critical. If we lost access to these, we'd be in deep doo-doo. Rare earths, indium, manganese, niobium, that's columbium, beryllium, uranium, cobalt, tungsten. I don't know how much is imported of those individually. But
I just thought that most of the uranium was imported at this point.
probably is, because we pretty well shut down our
Yeah, we
uranium
pretty much
mining
shut it
industry.
down.
Yeah,
Because the largest was in Arizona,
right.
and that's been shut down.
And so different mineral commodities are going to be strategic for different countries. For instance, China is very short of copper and has no chromium or platinum. Europe, highly industrialized group of nations, has almost nothing in terms of its needs. I mean, mine's a little iron and a little coal and stuff, but nothing.
Is that focused mostly on Western Europe, or does it include Eastern Europe? 'Cause I would've
No,
thought
that would
Eastern
include
Europe-
mainly Western Europe.
Yeah, I would have thought Eastern Europe would have a lot larger mineral deposits and
Pol-
availability from Western Europe.
Poland, and to some extent the
Yeah.
Ukraine, and that's about it. Copper and coal in Poland.
I was
um,
thinking Poland specifically.
And talking about strategic minerals, in 1925, a geologist called C.K. Leith predicted that World War II was on the horizon, and he said that the lineup would be the USA, the USSR, the British Empire, and French Empire against Germany, Italy, and Japan. And he said that because those first four had access to nearly every mineral they needed, and the other three had access to only one or two they needed. So his prediction was that they would go to war to get what they needed. And so right now we have a country that's sort of doing that. China has this go outside policy, which puts assured access to strategic minerals as a centerpiece of its geopolitical strategy. And they're moving aggressively to get mining concessions all over the world, and even to buy mining and oil companies, Occidental and Rio Tinto. That was vetoed by the Australian and American governments.
Yeah, but they're being very aggressive in Africa.
Oh yeah, terribly aggressive in Africa. Causing a lot of resentment in Africa. This has increased the nervousness of our security community, which remembers what Leonid Brezhnev said in 1973, that if they could control the Persian Gulf and Central and Southern Africa, we'd be in deep trouble. And so these three statements together are very, very worrying. One country feels threatened and is taking steps to deal with it, which is making other people feel threatened, and they're remembering real threats in the past. And it was exactly this kind of thing a lot of people think that led to Pearl Harbor. The Japanese foresaw that America would cut off their oil supply and decided to act proactively. So it's not, you know, I'm not personally terribly worried about this, but it's not very encouraging scenario. And again, their growing control of important mineral resources could enable China to deny imports to the United States. And we know they will because they've already done it to Japan in 2010.
Well, they've actually already done it to the US as well.
Well, that's
Restricted.
part of a more general policy where they
Yeah.
cut down their quotas here. That's part of the quota reduction. But Japan, they shut it off because the Japanese impounded a Chinese fishing boat or something. This is just a geological thing for anybody who's interested about the type of ores. And because they're getting it as REEs as byproduct of iron mining, their costs are very low. So they undercut Mountain Pass Mine in California, which was supplying over half the REEs to the world, and drove them out of business.
How we ought to
Yeah, but
define
they're reopening
RE.
that.
Rare earth elements.
Yeah.
They're reopening that.
They are reopening it. Yeah. They've already started reprocessing stockpiles.
Yeah, through significant concessions from
Right.
Congress, right?
Right, but the real issues are that consumers of rare earth elements have moved to China in droves to ensure that they have a secure supply. And that has caused the destruction of the supply chain in all the countries of the West. Mining, refining, purification, separation, fabrication, all gone. And it'll take years to reestablish that. And that's what Steve Jobs basically said to President Obama a year ago. In the meantime, of course, we're getting a rare earth rush, just like a gold rush. And people are working on advanced exploration projects in all of these countries, including some pretty weird ones like Greenland and in Vietnam. We're exploring in Vietnam. And Estonia, where the Estonians are beginning to reprocess the waste from the alum shale, which is an oil shale that's full of uranium and rare earths. So they already have a mess with all this uraniferous waste that's going everywhere. So now they're going to start spreading it around some more. So if these exploration projects are successful, we'll have a bubble in rare earths, which will depress the prices for many years. But as I say, the real issue though is who's going to process them and fabricate them. And then also the problem for these ventures is lots of radioactive thorium and uranium, very high energy inputs, very high, needs a lot of acid and lots of water. So there's a lot of environmental objections when you start. They just opened a new processing plant in Malaya over everybody's dead body. And here's the production of commodities by value. Remember the volume one was sand and gravel was way ahead of everything else. Here's gold is ahead of everything else. And I think personally that it's not because we use that much gold. It's nervousness about world affairs. It's nervousness about the future. People are buying gold. And that's what's sustaining this huge run-up in prices in mining. The next three are all 20th century minerals. These things were not significant before the beginning of the 20th century. Bauxite, cement, chromites. Then we get to some of the traditional ones, iron ore, silver, copper, clays, rock shale. So this is really interesting. We got one which is a store of value, but the next three are all brand new.
Those three just mainly for construction?
No. Well, cement is, but bauxite is used for everything. That's aluminum. That's what you make aluminum from. And chromites are used for specialty steels and all kinds of alloys. Chromium is a very good alloying material. New capital production required. I happened to hear a talk last month, and the guy said to bring into production 1 million barrels a day of new oil at the present moment takes $100 billion in capital. And that's what's being plowed into the deep water in the Gulf of Mexico and offshore Brazil and places like that. by comparison, the investment in new greenfields iron projects in 2010 was 28 billion. Gold, 7 billion, copper, 6 billion, rare earth, 3 billion. And the total invested in new mining projects in 2010 was 562 billion. An enormous number of billion-dollar projects in Latin America in particular. And so, and this excludes China. So this is 6% of the total world funds available for investment. And that's not counting the oil and gas investments. And it's 4% of US GDP, and it's going up exponentially, whereas GDP isn't. So, so it's real costs are probably slated to go up. And this is just, I think that's, have I already shown that one? This is the concentration, oh no, this is not the countries, this is the concentration in the industry, where Codelco, the Chilean nationalized copper company, produces 11% of the world's copper. And the top 3 companies produce 27%. Iron ore is worse. The top 3 companies, which is a nationalized company in Brazil, the Vale Group, quasi-nationalized, Rio Tinto and BHP, between them produce 41%. So real prospects for some monopolistic control if they can ever get away with it. And just a word about titanium, because it's a classical example of this concentration. 25% of the world's output comes from one mine near Durban in South Africa. The rest of the continent of Africa accounts for another 25%. Titanium occurs with zircon occurs with titanium. That one mine accounts for 1/3 of the world's zircon supply, and also high purity iron. Because of this concentration, people have been looking for new titanium deposits, and an announcement has been made in South America. And the uses for titanium, this is the one replacing lead, with bright white pigment for paints, paper, toothpaste, plastics. And the metal, which is only 5% of the total output, is used for aircraft engines and frames. There's some numbers there, and in specialty steels. Yeah?
What is that? Is that the way they
That's,
silo?
yes, these are silos. There's probably a huge conveyor belt somewhere out of sight there, but they mine fossil beach sands in huge volumes because the heavy minerals that contains the titanium are only about 5% of the sand. So they're running all this sand through, and they're stockpiling the heavy minerals, that's why they're dark, and they're running the sand bank to, and fortunately that's a case where you can do some restoration. So,
And another oxymonolistic is lithium and palladium. I think it is.
yes,
For lithium batteries, it's almost the whole source.
yes, one salar, one playa in Bolivia. And I'll just very quickly just run through this. Titanium metal is produced by sacrificing magnesium. First you produce magnesium, and then you destroy the magnesium and get titanium in a complex chemical process. The United States used to be the main supplier of magnesium. Now it is China. So China is basically in control of our titanium production as well as 97% of our rare earth metals production. So, and I kept running into this all the time. I think I'm going to skip these since...
John, you want to take a break and get
Yeah,
by?
yeah.
And we can
I think I've got about 3 or 4 more slides left. That's all.
Okay.
So, this slide here shows us a standard supply-demand diagram with various levels of demand shown as these D curves, and the supply curve here. I've just shown one supply curve. And what I'm showing is that the usual economic dogma is if you increase the price at the margin, the supply will go up. And if you decrease the price at the margin, the supply will go down. So here's the situation: smoothly increasing price as demand goes up, the supply smoothly increases and the price goes from P1 to P2. But the trouble is, as we're seeing now in the oil industry, you get to a level here just above D2 where industries at max capacity, everything's maxed out, and the supply cannot be increased any further without a new mine. And we're looking at, as I say, situations with mines representing 10% of the world's supply. So, and they require a huge investment. So the price is going to go up and up and up. So as demand goes up here to D3, the price has just shot up, but the supply has not increased at all. Get near D4, and people are scrambling around. Maybe recycling has increased, but there's a little more supply there. For instance, a good case of that would be stealing lead off church roofs, which is rife at various times, and they're stealing copper off church roofs right now. And then
people and other people's
and other
air
people's.
conditioning systems.
That's right. That's right. So that's increasing the supply at the margin here. So then, okay. So now let's assume now that we go that the price has gone up so much and stayed there long enough that we brought a big new mine into capacity, or more than one big new mine into production. And so the supply is now increasing. And the trouble is that even if the demand begins to increase, we now have a situation of oversupply. So going from D4 to D5, which is an increase in demand, because we can't shut down mines easily, and that's something I haven't said before, it's really hard to shut down a mine. If it's an underground mine, it floods, and also if it's a surface mine. So people try and keep them going even when they're losing money. So here you have a decreasing price. And I call this a lumpy supply curve. Another word for it would be a stepped supply curve. And it comes from the fact the supply is inelastic for a period of up to several years or a decade. And it requires, to overcome that resistance, it requires this huge investment of 20 billion for a new copper mining complex in the Andes, and 25 years, because even in the Andes, the local Indian tribes are now saying, you can't do it. You can't come in on our land and mine copper. So it's taking, most of the 10 years is maybe doing the engineering and the preliminary work. The other 15 years is getting permits. And as I say, the reverse is true. If overcapacity develops, then you can't shut it in, and you have to wait for demand to grow back to capacity. And I will talk about the porphyry copper. POCU stands for porphyry copper, shorthand. And this is a case. This is a small new mine. This is Oyu Tolgoi copper gold in Mongolia, discovered in 2001. By 2020, the amount of capital expended will have been 10 billion for 3% of the world's copper supply. And the mine will represent 30% of the GDP of Mongolia. That's the kind of thing we're looking at. And this is, of course, this makes it, when you're 30% of the GDP, you imagine the scarcity you're causing in other parts of the economy. And this is a low-cost mine, essentially, because it's right across the border from China, and China's the market. It doesn't have to have a railway up to 20,000 feet in the Andes, and it doesn't have to have a port developed on the coast. They just ship it into China. But that was an example that was in The Economist last month. So this is an illustration for copper. This is what we're going back to 1900. This is 2000. This is the new century here. And what the grade has done. First, we were mining high-grade veins. Then we started using mechanical equipment, using more energy inputs. We went to skarns, which were lower grade and bigger. Then we went to these big sedimentary copper deposits that I worked on in Zambia, 2% copper, and the grade went down. And finally, we started bringing in, finally, massive sulfides started being used, which are another volcanic type of deposit. And then finally, porphyries, these huge giant things in Chile and in mountain ranges over the world. And the grade now is flattened out at about 0.05%. No, 0.5%, I'm sorry. 0.5%. Meantime, production, although it's kind of jagged, has been going up exponentially, except for an interval between 1968 and 1980. And that interval represents an interval of declining production in the old sedimentary copper deposits, which were getting too deep to work. And we hadn't yet brought in the porphyries, got the porphyries on full production. Meantime, the price for these low mechanical inputs, much human input, so wages very high, very expensive to produce from the small deposits. Then they reached around 1930, a low point in the depression. The prices began to climb, and then the sedimentary coppers, as I say, were getting difficult to work. Underground. So then there was a transition to open cast mining, which brought costs down again a bit. And then the porphyries started to come in, and they came in and drove the price really way down because they're very cheap to mine. And now, in 2000, the commodity markets began to realize we hadn't discovered many porphyry coppers recently, and we were looking at a future scarcity. So the price started to climb, and that's where we are now. Meantime, the land disturbances were rising. This is schematic, but I'm showing them rising
John?
exponentially.
Yeah,
Yep,
so what you're illustrating there, where the big price spike starts,
yep.
that's where, out in 2000, is that the point that the industry
This
bought
one.
into the theory that there was definitely going to be a shortage?
I think more the commodity markets.
Okay, so they started bidding it up.
They started bidding it up.
Speculators bid up the
Yeah.
price.
But it's real because you can see what mines there are in the world, and as I say, it takes 25 years sometimes to develop a mine, 10 years minimum. What was it for Bionovo? So you can see what's coming down the track, and they can see that the shortage is coming down the track way ahead of time. And this is this inverse supply-demand curve when people are still bringing on porphyries because they went out. What happened at this point in 1970 is they figured out how porphyry deposits were formed and how to find them. So everybody went looking for porphyry coppers, and all kinds of projects started, and they were committed. They spent billions of dollars, and they couldn't stop them. So the price kept going down and down and down. And of course, eventually they stopped them. So now the price is rising. So it's this is the second from last slide. What are we looking at that might change some of these ideas? Well, iron oxide copper gold deposits are about the same grade as porphyries. This is the copper. They contain uranium, and they contain some rare earths. And they found this huge thing in Australia, South Australia, and everybody in the world is now out there looking for IOCGs. So far, we don't understand them, so we haven't found. I think there's 2 more real, genuine IOCGs being found. One in Chile, and perhaps one in Baja California. Then the next thing down the line would be seabed manganese nodules, and these are a layer a few inches thick on the bottom of the ocean.
Oh,
And
see,
they-
I knew that.
Right, and their grades are similar to porphyry copper, but they're much more inaccessible because they're in very deep water. And what I wonder is whether we'll ever have. We might have some small production from manganese nodules, but I don't think it's environmentally permissible to go mining them everywhere.
So compared to deep sea, drilling, for oil,
Mhm.
how more deeper, or how deeper?
These things essentially are in the deep ocean, so they'd be at this sort of 10,000 feet deeper than we drill for oil. Yeah, deeper than we drill for oil. New mining technology. We've got things like solvent extraction and electrowinning, which does away with these nasty, dirty smelters. But unfortunately, the energy costs are about twice what they are, and they use things like sulfuric acid a lot. So you've got, and also cyanide. So you've got potential problems with losses, with leaks. Another thing that's being done in Canada in the Flin Flon nickel belt is everything's being done by remote control from the surface, no men underground. just completely machine controlled. That's very capital intensive, of course. And then also solution mining is being used for uranium, it's being talked about for copper. But you have to control, and it's also used for things like potash in England, which is again the fertilizer mineral. But it tends to be very energy intensive because you're pumping huge quantities of water through the ground, and you probably have to frack the ground in most cases. And you have to control, you have to make sure that the fractures and faults in the ground don't allow the solutions that you're pumping through there to get outside your ore body. You don't want them getting into anybody's wells or anything. So that's technically complicated, and it can be very energy intensive. The potash mine in England that uses solution mining has a shaft, and to make that shaft stable going through all the salt deposits to reach the potash, they have to freeze the ground all around it for 4,000 feet and keep it frozen. Substitution is ongoing, and I didn't put titanium construction materials on here because the energy cost of titanium is so high, but we are using carbon composites, and we will use more of them. With the new airplanes are going to be largely carbon composites. Nanotubes in someday will reach volume production, and then the organometals and things like that. And this is a zinc solvent extraction plant, big huge thing with vats full of acid. So my conclusion, I'm missing one slide there. I had one slide which actually compared the energy costs of, I don't know what's happened to it, but use 800 kilowatts for conventional smelting for copper. And it takes 1,400 kilowatts for electrowinning. So it's using the acid and not having the smelter. And it takes 2,700 kilowatts to refine titanium from the ore. So it's 3.5 times more energy than copper. So these are the conclusions. No immediate threat of exhaustion of any important commodity. My guess, and the guess of several papers I read, was that we'll start seeing seriously increasing real costs around 2050. That's when things begin to look a bit strange. Part of the reason that economists have such a rosy attitude is they ignore this thing, and I put it in there because I haven't seen it anywhere else. The lumpy supply curve, which puts these huge price fluctuations in that can be quite long term because of the few large deposits controlling supply, the capital requirements, the time requirements, and these exploration bubbles, such as we saw for porphyry copper, we're seeing now for rare earths. We saw it in the 80s for epithermal gold. Population and economic growth is exacerbating the problems, meaning that the deposits get larger and lower grades, so more and more capital, more and more environmental complaints and hearings and time, and people saying, no, not in my backyard. More and more political risk because the biggest deposits may not be in the most friendly countries. Technology is leading to the use of more and more exotic materials, which causes increased refining costs, increased energy usage, increased environmental costs because these are generally low grade and they use some nasty things to process them. And then in the long term, we still are dependent on this race between technology and resource depletion. And since 1800, technology has been winning, but as grades go down, particularly in the frontier, goes away, I think, and I'm not alone in thinking this, there's a school of economics which also thinks that the long-term curve will be decreasing real prices and then a gradual increase. And then, but more important than all of that, I think, is the environmental constraints. Land, the external costs that increase as multiple exponential functions multiplied together, and the issues of land availability. I think this is going to be the major constraint long before the actual ore grades and things become limiting. And so, as I say, 2050 we start to see serious limitations on mineral available. Thanks. That's it. There's no picture of me at the end here.
Landfills for aluminum and tin,
Well, not aluminum, I don't.
whatever else can be found in the trash.
Yeah, you know, we might do that. I mean, in some sense, we already have done a lot of that around mines. When they started up the big mines in Zambia, the efficiency of ore recovery left 0.9% copper in the tailings. And in the 90s, they went through all these tailings dams that used to be part of my life are all gone. They went through and with more efficient processes and got a lot of the copper out. And that's, so where there are concentrations like that, we've been doing that. And I think definitely landfills will be one of those places. I mean, the best thing, of course, is what Austin is doing, is you keep it out of the landfill in the first place. You know, 100% recycling, or whatever they call it, total recycling. Yeah. And there's, I mean, I didn't talk about recycling at all, because what I was talking about was the new mining and its exponential increase. There are some economists that say, well, you know, we've got recycling, and all of this stuff about exponential growth won't happen because we'll recycle, but it is happening, and it hasn't shown any sign of slackening off. So I decided, in the interest of being able to give it all in one talk, so I wouldn't talk about that.
So this is a little off topic, but you know the theory that the peak oil.
Yeah.
Are you? What's your?
Well, we're there. I showed that on that one graph. I mean, it's not a peak like a mountain peak. But it's
So peak is in 2050. 2050 is the end.
2050
No.
is when price reverses.
in 2050. I just think that we'll start seeing increased real costs. And I mean, I should have been more explicit. Around that time, somewhere around that time, we'll see that our purchasing power is being severely crimped, because everything with any mineral content is beginning to cost a lot more than it did before. So that's, you know, absent revolutions and all the rest of it, that's what I think will be the real, there it is. What's happened in the last 9 years is that we haven't increased oil production at all. We reached this point in 2003, and production is horizontal with a lot of little blips on it. But this is peak oil, we're in it. Yeah. Now, I mean, you know, if you go to Exxon, they'll say, oh, but we've got all kinds of unconventionals. We'll go to oil shale mining, and we'll go to fracking, and we'll go to this, and we'll go to that, and tar sands. But in actual fact, we can't take advantage of a lot of those things. Number one half of the tar sands reserves in the world are in Venezuela, and we don't talk to the Venezuelans. And the other half is in Canada, and we've got a huge environmental lobby which is determined not to have the pipeline that we need to bring the stuff down here, so that will, in fact, shut down the tar sands operation in Canada. The environmental lobby wants it shut down. They don't say that. They focus on the pipeline. But if the pipeline isn't there, either the stuff will be pipelined through the Rockies, which is going to be even worse, to the Chinese market, or the mines, the oil shale mines will be, tar sands mines will be shut down. And the same with the fracking, although the complaints now are mainly around gas fracking in New England, but you know, there's a growing outcry about fracking, and that's really our last hope in this country, because those are the source rocks. We're now attacking the source rocks, and if we the situation with that is, you hear we could be self-sufficient, but to be self-sufficient, we'd have to put, you know, something like 1,000 drill rigs into the oil fracking thing, and we'd reach self-sufficiency in the next week. Production would be going down, and we'd lose it. A better way is to aim for some reasonable level of production that we can then keep it at plateau for several decades. That won't be self-sufficiency, but it'll be a lot less oil imports than we have now. And the guy that gave the talk about that I heard suggested that it would be the bankers that would enforce that, not the government. Bankers would look at if a rig owner or an oil field developer went to them and things were going up too rapidly, the bankers would say, no, I can't justify lending you the money. So,
They
yeah.
don't have enough money to finance it themselves.
Well, that could happen, but I don't know.
Okay, thanks for that.
But I think energy is the real constraint.
Apple ones.
I think many of the things that people talk about in terms of new wonderful alloys and minor metals and titanium construction materials, I think is one of them. These are fundamentally going to be limited by the amount of energy required to move in that direction. So one suggestion would be is we develop the technologies to use those things in a way that we can use intermittent power supplies like the sun or the wind. Whereas in the 20th century, everything was aimed at making continuous processes. My father was a metallurgist and worked a large part of his life in getting away from batch processing in making non-ferrous alloys in order to make one long continuous billet of copper that never stopped, 24 hours a day, 7 days a week. That would require fossil fuel for most metals in huge abundance. What we would be much better would be go to a batch process when it's sunny and you can generate power. You melt up a batch, you make it, you do whatever you're going to do, and then when the sun goes away, you shut it down.
But then you still have to transport it.
Hmm?
You still have to transport it.
Yes. Well, that's a big issue. But hopefully, we have a lot more natural gas than oil, and if we move our transport fleet to natural gas, we won't necessarily be hindered within the next 30 years by transportation issues. We just have to get the national will together to do that. So, okay.
Any other questions?
Any more questions?
Thank you, John. Appreciate it.
John?
Thanks, John.
Thank you. Sorry I took so long.
No, that was fantastic.
Real quick before we, I guess, wrap